Morning, everyone. Welcome to this coffee break. Happy to be here once again. So today we'll discuss air cooler. So whether you're a seasoned analyst, asset owner, or just want to know a little bit more about tubing inspections in general, air coolers, you're curious, I'll try to cover a large spectrum of information. So I'm pretty sure you're going to learn something. About myself, I'm David Veilleux. I'm the product manager for the tubing product line at Eddyfi. So what do we do? We have a complete inspection tools for tubing inspections, many techniques, acquisition system, acquisition analysis software, and the probes as well. So today, let's get started with the air coolers. I will click here and should be good. So also known as the fin fans. Air coolers are found in petrochem. Lots of assets have them, various processes, but also in natural gas pipeline compressor stations. So as you can see, on the picture, we've got 8 gate of the fin fans on that compressor station. So this is another place where we can find a lot of them. What is special about the air cooler? That's a neat exchanger, of course, but it's got a few things that make it quite challenging to inspect and a little different, and they need to be addressed accordingly. First of all, it's above ground access. So imagine there's the little ladder. You need to climb up there to get access to the tubes. Once you're up there, then there's only the catwalk to put your gear there, be ready for the inspection. So reduced, limited space. Once you open up the first tube, well, you don't have access directly to the tubes themselves. There's the header box. The header box is an empty region where the fluid gets transferred. So this is there, and it's about 8 to sometimes 16 inches, varies in length, but still the tube do not start already there. You need to pass through the header box to access the tubes. And once finally you get to the tubes, these tubes are a bit tricky because they're made of carbon steel. So this is a ferrous material, and they have on the outside to maximize the heat transfer with air. They've got aluminum fins, sometimes other material, but the fins on the outside are there to maximize the heat transfer. So to inspect those, one of the inspection technique that is often used is IRIS. So IRIS is using the ultrasonic technology to do this. We've got a turbine spinning in the middle, so the UT signal bounces on the mirror, and we do have a complete CT imaging of the inside of the tube. So IRIS offers really very accurate wall thickness measurement. It's got also full sensitivity near support plates and tube sheets. And it's a perfect proof up for electromagnetic testing as ECT and RFT. However, IRIS, as you might think, offers a few challenges that are even bigger challenges when we come to the air cooler inspection. So first, carrying the gear. So you need to bring everything up there. So the turbine, everything, the pump, and etc. So it's an extra burden. Second, we've got the tube cleanliness. You know that to inspect those tubes, sometimes there is corrosion inside, deposits. So we need to make sure they are clean. And IRIS is the technique that requires the most cleaning. So for an asset owner, so an inspection company getting there to do the inspection will face this, and it's quite a burden for some asset owners to do a proper cleaning for IRIS to be used. We need clean water, so if there are debris or scale or deposits at the bottom, this influences the results we get as the UT signal is triggered by those defects, those pieces that are in the water. Then to flood the tubes, you need to get the water, so it might be quite a challenge in itself, bringing the water all the way up to the catwalk. Flooding the tube through the header box. Remember this space. Well, imagine if you're trying to at the same time make sure your tube is flooded, but you don't have access to it directly. It can be an added challenge. And IRIS is a slow technique. So for any IRIS inspection, this will be the slowest one. You need very precise pulling speed and very slow. So we're talking 1/3 of a foot a second, or 0.1 meter per second. So what are the other things that could be inspected? So of course we could think that remote field testing for carbon steel, this is really good. However, there's a major deal breaker here that are called the fins. The fins on the outside block the remote field testing to be used. So we need to look at the other opportunities. So the next one is going to be near field testing. Near field is a little bit the same principle as a remote field. However, we bring the receiver and the drivers closer together, and so we only measure or see the inside signal, the inside response of the tube with this probe. So it's easy to use, so it doesn't require any magnets. It's unaffected by the structure. We only see the insides of the tube. So whether you have a support plate, fins, tube sheet, it doesn't impact the near field results. And it's faster than IRIS. We're talking about 1 foot a second, about 0.3 meter per second. However, the drawback, the limitation of NFT is that it's only amplitude-based sizing. So what does that mean is that if we get an indication, we'll get a response, a signal response. But if we compare two indications with the same signal response, we will get the same amplitude. And that means that the defects have the same volume. So that's what we're reading. But you know that the same volume doesn't mean the same report entry. So a large 20% defect gets the same response as a deep 80% defect. It's easy to understand that which one you want to make sure you add to your report. It's the deep 80%. You want to make sure that you see those indications. So this is what is difficult with NFT, is making sure that even though there's a large amplitude, is it because it is a large defect or is it a deep defect? So that's where we bring in NFA. So we got near field with array capabilities. So we introduced this technique. So we added small coils so we can get C-scan imaging. So first advantage of this is we're using the NFA near field testing to see what's inside, so not affected by the outside. We bring in C-scan imaging, so better information on defect morphology. So for those signals, we get track detection, so major advantage there. And it's the same speed as a near field. So a medium acquisition speed, about 1 foot a second, so 0.3 meter per second. This probe is built for the field. It's built sturdy. We got the wear rings. It's hardened steel and they're replaceable. So they're just a little bit bigger than the probe. So the sheet gets protected. And we know carbon steel sometimes can have rust and be tough. So those wear rings are there to prolong the life of the probe. We also have the stainless steel protective sleeve. That's added layer. When we're talking about NFA, the fill factor we're looking at is about 86–87%. So that gives an idea on the place required. We do have standard diameters for about 3/4 of an inch to 1.5 inches, different thicknesses, but these are the most standard ones, standard products we have. We have many different diameters for that. And of course, if for special cases, we also have custom availabilities. This is a one massive NFA probe that we've designed just for one client. So this is something to keep in mind for special applications. Go back to the defect morphology. How does it translate for the NFA signal? So the field here is so this is the example. So we got near field on the left side and NFA, and you see that for a defect response like this, you see that on the NFA will give you two very clear indications. So that gives a lot more insight on what is going on in this tube. Same here at the bottom. Those small indications are in reality 3 independent pits. So that's the value here. It's getting to know more, having a better insight on the indications. This is another real life data that we have. So we can see we are able to detect the taper erosions with the standard bobbins in there. But everything that is the rest with the pittings, we have a better idea here of like what type it is, where this is situated. Does it seem to be deep, all concentrated, or spread across a large region? On the crack detection, so here we had a tube that we scanned in the office in our lab. So that's a calibration tube. So we see we have a few cracks in there. So the first top 3 are ID cracks. One is through wall 100%. And then at the bottom, we got OD cracks. And then at the very end, the ID groove 20%. So iris, we first scanned this tube with iris, and this is the result with iris. You see that it is limited in detection capabilities for cracks. You notice here we were not able to pick up any of the defects. The only one we were able to see is the ID groove at the bottom. Once we pull out with the NFA, we were able to see the first crack 100%. You notice here the signal compared to iris. The second one at 60%, it was ID. So still a pretty deep defect. We were getting the result, the signal response. Next one, ID crack 20. Honestly, this is very small, so we were not able to pick it up. And then keep in mind that these are 0.5 millimeter width cracks, or 221 thousandths of an inch width. So these are very, very small. As for the OD crack, well, as expected, we were not able to pick up any of those as they are outside and they're very small defects. But neither was the iris capable of detecting those cracks. So we see that it really offers a lot more for the crack detection. So than compared to iris. Here's another example, real life example of a circumferential crack at the tube sheet. So we got the signal from the tube sheet here, and very clearly on the C-scan, we have the crack. All this info, a little bit more details. If you like to see, get access to those data, pictures, etc., please visit our website. There's a blog on it. My colleagues Antoine Grégoire and David Veilleux did a very good job at scanning those tubes and showing you the advantages of NFA. I want to bring out the point that yes, the NFA is good. The NFA is great. We get C-scan imaging, defect morphology, and also crack detection, all of that to the speed of NFT without the hassle of the water. But that doesn't come alone. You know, when you're doing the inspection, yes, the probe needs to be very good, but the probe is connected to the acquisition system, and the very good partner for this is the Octane battery operated system. So imagine on the catwalk up there, no need for electricity. You got batteries up there, so this is a major advantage. Also, the hectane is made for the field, rugged, but also capable of doing many techniques, from array to iris to ECT, RFT, MFL. So we cover all the techniques also for surface applications. This is combined with Magnify, or acquisition analysis software, where you get those nice 2D scans, 3D scans, to do a good analysis, get those defects out. And finally, whether you're asset owner, inspection company, all this artwork, all this attention, this expertise that you have in analyzing the data needs to be put in a nice report that reflects all the artwork that's in there and the analysis that was done. Best tool to do this is 2Pro. So we integrate 2Pro in our solution. So we get a direct link, and the data can be fed in there. You get report templates that can be used, and a 3D model that can be designed automatically. Once you create the tube sheet, you get the 3D model, and the asset owner will have extra information, more details on the pattern of defects. Where are they located? Is it near support plates? Are there flow issues? So it's really appreciated from the asset owners to get those this extra model for better insight. So our solution is not just about the NFA Pro, but it's about all those products working together, and it offers speeds, superior data, and insightful reports. If you want to keep learning more about our products, the best place to go, Advanced Tubing Solution. We can see there. You can see what more we can do with the ProBot and other probes. We also have eddy current array probes. If you want to know more about Iris, yes, we do support it. It is fully capable, magnified, of analyzing Iris data, and it's a very good complement to the electromagnetics, and as well EC probe, etc. So that's wraps up a little bit my presentation. I'll take the questions. I see quite a few people here from Gabon and Nigeria. So thanks for coming out. I see the first question I had was how clean the tubes need to be to use the NFA. So NFA, I would say ECT clean. So when we're talking about tube cleanliness, Iris is the most cleaning you need. RFT will be the least, and I will go in between, where NFA and ECT are comparable cleaning requirements. Next question we got is, can it be used on mildly ferromagnetic materials? Yes, it can, but we don't have that much results or real life experience with that. However, we do have another probe that is very designed for those applications. It's the full saturation bobbin probe. So if you want to know more, check out the Advanced Tubing Solution page or the website. We have a lot of information of this. This is a great port. Really appreciated for all those duplex inspections that can be tricky. Next one, is there a difference in phase angle between defects of different types? Only from cracks. Cracks we will notice a little bit, but normally pits will all be on the same plane. There is no phase separation with near field. It's only crack that we will see some shift in the phase angle. What version of hectane do you need to use this probe? So this is an array probe. You need the what we call internally the 64 options. So if you're the owner of an hectane 2 ERNMI doing a lot of tubing inspection, you want to upgrade, you'll need to upgrade your machine to the 64 options. 64 option is the big connector, array connector. And it gives you access to any of the probes from NFA. Also, some of the Eddyfi probes, it's really up to 64 channels. Our standard Eddyfi probes, pretty much 3/4 half of them require the 128 options. But for NFA, you need the 64. And with the 64, you can always have access to surface probe as well. And keep in mind, whatever octane you got right now, it can be updated and upgraded to 64, so you can have access to this this probe. Do you plan to add a calibration group support to magnify software? Not sure exactly. I would need a bit more details on that question. I would say different. You mean for the NFA or only software as general? Normally, if we have a calibration group support, we can separate the folders in calibration groups, in cal groups we call. So this is the folder structure that we have. As for the cal tube in themselves, they can be set up using the wizard. We got menus in Magnify where you can adjust the sizing curve accordingly. But if my answer is short or you want more details about this, don't hesitate to contact me or the team to learn more about this, and we'll sure do support you and help you get the information you need. So I see another hi from Colombia, Algeria as well. So hi everyone. So the next question from Abdul: fill factor required for best detection. As again, 86 to 87%. We like to. NFA likes to be like a larger fill factor is going to be good, but as always with tubing inspection, too big of a fill factor is a bit dangerous. So as to get the probe stock and everything. So, but 86 to 87%, we have good results with them with those fill factors. So, are there any other questions? So again, you see on the screen, if you want to reach out to me, it's my email address. If there are no other questions, I say thanks everyone. That was the last official coffee break of the season. Take care everyone, and meet you probably in the fall next time. In the meanwhile, reach out to us if you have any questions.